What's up, nerds? You guys miss me yet? Of course you do. Especially when we're going to start talking about absolute value graphs. Yay! Think Kermit arms. All right, so the good news is these are really, really easy. Okay, so an absolute value graph has a parent graph. Okay, real simple. The parent graph of the absolute value function is f of x, because that's just generic function notation, equals the absolute value of x. All right, now before we go any further, I really want to advise you, as we are working our way through all the absolute value stuff, please make sure that you make your absolute value bars really, really long, okay? The most common airheaded mistake that people make is they make their absolute value bars really short, and then they get confused and think that it's 1x instead of the absolute value of x. So let's not make that mistake. But this right here is the parent graph. Okay, it's going to have a vertex at the origin, 0, 0, which means that it's going to pass through, you guessed it, the origin. Okay, so what does that look like? Well, it's going to go through the origin, and it's going to have the right side of it is going to be this nice, pretty diagonal line, and the left side of it is going to be this other nice, pretty diagonal line. And you'll notice that absolute value looks a lot like a letter. Oh, the absolute value looks an awful lot like the letter V. V for Vicchio. V for victory. Saving Private Ryan? Anybody? Anybody? No? All right, moving on. So you guys have this foldable on absolute value graphs, and we're going to use that as our notes to kind of work our way through how it's similar to the types of functions that we've already learned how to graph, what those different transformations are, and then we'll work through a couple of examples. All right. So if you look over on the next little page of it or rotate it around, we've got the transformations. Okay. So this should look very familiar to you. All right. When we did square roots and cube roots, it was basically the same thing. Just replace these absolute value bars with a radical, and it's all the same thing. All right. So let's go through the transformations one at a time. A can be a reflection or a dilation. Okay. The reflection is over the x-axis. And that's when you're asking, really, is it positive or is it negative? If it's positive, it's going to be a V that kind of opens up and look like the actual letter V. If it's negative, that means it's been reflected over the x-axis. So it's really going to look more like an A-frame or an upside down V. All right. Dilation right here is really the fancy math word we have for a stretch or shrink. Okay. If the value of A is greater than 1, that tells you that it's going to stretch. Okay. It's going to get pulled up. If the value of A is in between 0 and 1, okay, that's going to be a shrink. And really, I guess I should say the absolute value of A is greater than 1, and the absolute value of A is in between 0 and 1. Okay? Because again, if it's negative, it's just a reflection, but its absolute value is going to follow along with these guidelines. Okay? A stretch is going to make it a skinny V. A shrink is going to make it a big old fat V. All right? So this H here is a translation, which is the fancy math way of saying it is a horizontal shift. And that's going to be the same for this type of function as it is for all of the other parent functions that we've taken a look at. It's always going to shift it left and right. Kind of like this K is at the same place, probably does the same thing. The K is a vertical shift. So it's going to go and move that function up or down. Okay, remember, vertically is going to be along the y-axis. So it's going to have a vertex. Its vertex is always going to be located at the point HK. Okay, keeping in mind that the sign of H is always going to be the opposite, because this little negative sign that's right here, okay, that's actually a part of parent graph. It's actually a part of our function here, okay? So the h is always going to have the opposite sign of what it is that you're actually seeing when you're poking around and look at it in the function. All right, so we're going to see the exact same transformations for an absolute value graph that we saw when we were looking at a square root, exactly the same as when we were looking at cube roots. All right, so let's start taking a look at a few examples. Okay, so we have example one, which is really part A and part B, and we'll go through and we'll do each one of these, but we'll kind of do A first, then we'll go through and do B second. All right, so it says to graph and describe an absolute value function. So if we're going to go and graph this, the very first thing that I need to do is identify where my vertex is. So I know that my vertex, okay, is always located at the point HK. So I need to identify HK within each problem. So this right here is where H comes from, and this right here is where K comes from, okay? So I take the opposite sign of H, because remember that negative sign is a part of the equation. So I'm just going to take the 2. So I have the vertex at 2. It's also, its y coordinate of that vertex is going to be -4. Okay, so 2, -4 is the vertex. We should be able to plot points in an algebra 2 class. So we've got our x, we got our y. So we go 2 units along the x-axis, -4 along the y, and that's where we have our vertex. All right. When it says opens, that means, does it open up or does it open down? In order to determine that, I need to look at the value of A, okay? If the value of A is positive, it opens up. There's been no reflection. If the value of A is negative, then it opens down because it's been reflected over the x-axis. In this case, we have a value of A that's +3. So because that's positive, that tells you that it's going to open up. The next part here is the slope, okay? So remember how when we looked at the parent graph, we saw that it kind of went off at almost like a 45-degree angle towards the left, and then kind of the same thing over on the right? Well, that all has to do with kind of the slope, and the slope actually comes from plus or minus A, okay? So the slope is plus or minus A. The value of A in this case is 3. So it's going to be +3 and -3, or rather +3 and -3. So what does that mean? I can use the slope to do the rest of the graph. So from my vertex right here, I can count up 1, 2, 3, and I can go to the right by 1. But then I can also count up 1, 2, 3, and go to the left by 1. Then from this point, I can go up 1, 2, 3, and to the right by 1. And on the other side, I can also go up 1, 2, 3, but now I go to the left by 1. So you see how I'm going and I'm creating these lines that when I play that super fun game called Connect the Dots, I'm graphing an absolute value function. Okay, could you go through and make a t-chart to do this? Sure, by all means. You could have an x and a y chart. You already know that the vertex is going to be the point 2, -4. So we could pick a number that's less than 2, say 1, and we could plug it into the function. So we do 3 times 1 minus 2, the absolute value of 1 minus 2, and then -4. So doing some arithmetic, 1 minus 2 is -1. The absolute value of -1 is +1. 3 times +1 is 3. 3 minus 4 is -1. So I should have the point 1, -1 on here, and lo and behold, 1, -1 is right there. Okay, I could go and I could plug in a number that was more positive than 2, okay? Say 4. Well, plug it in. 3 times the absolute value of 4 minus 2 minus 4. And if I do some arithmetic, 4 minus 2 is 2. The absolute value of 2 is +2. 3 times +2 is +6. +6 minus 4 is 2. So I should have the ordered pair 4, 2 on the graph. And lo, there it is, 4 and 2. So instead of having to go and do these t-charts where you got a lot of arithmetic that's in there, you can just kind of use the slope and say it's going to be plus or minus whatever that value of a is. All right. So now that we have this first graph done, let's go and do the second graph here. Okay. So the second graph B says y equals -1/2 times the absolute value of x plus 3 plus 2. So the first thing I want to do is identify the vertex. So that means I'm going to need to pull my h and my k, but it's always the opposite of h. So there's supposed to be a negative in here, but I don't see it. And that's because two negatives make a positive. So the vertex is actually at the point -3, +2. Okay, opposite sign, actual sign. To determine how it's going to open, I look at the value of a. I see that it's negative, so it's going to open down. And the slope is going to be plus or minus 1/2. So let's go and just use this to graph it. That way we don't even have to mess with a t-chart. So my vertex is at -3, +2. So it's going to be located right about schmear. And then for the slope, I'm going to go down 1 and to the right 2. And then I'll go down 1 and to the right 2 again. Could I keep going down 1 and right 2 all the way to the edge of the graph? Probably. Okay. Is it necessary? Nah. Get 2 points in that direction. We'll call it a day. But then we also have to go the opposite way. So we have to go down 1 and left 2. Down 1 and left 2. And you can see we're already off the graph. But if I play my super fun game called Connect the Dots, then we have this other absolute value graph. Okay. Because its value of a is -1/2, it's opening down. This definitely is opening down. Because 1/2 is in between 0 and 1, we can tell that it has been shrunk. It's been smushed together. That's why it's wider. Okay. So hopefully doing sketches of these graphs looks pretty easy for you guys, because let's be honest, is real easy. Okay. Basically, can you graph a couple of lines in the shape of a V? If you're graphing something and it doesn't look like a V, you done messed up, son. You done messed up. Right? So next, what if we have been given a graph and we have to go and write the absolute value equation? So that's what example 2 is all about. So let's take a look at these two and we'll do them one at a time. So if we look at example A, we need to identify all the important things about it. Well, I can tell that this point right here is my vertex, and it's labeled as 2, 4. So this has to be my value of h. This has to be my value of k. There's another point that's been given to me as well, and that's 3, 1. Why it's important is because that tells me that from the vertex I went down 1, 2, 3, and to the right 1. So what's the slope of this part of the line? Well, that would be -3. Okay. On the other side, I would go, down 1, 2, 3, and left to the 1. So that would be the same as going up 1, 2, 3, and to the right 1. But I'm kind of focusing on this one because I can see that this opens down, so I know that it's going to be negative. So I know what the slope is. So that tells me about the value of a. I know what the vertex is, so that tells me what h and k are. So don't I have literally everything? Because isn't it f of x equals a times the absolute value of x minus h plus k? And don't I kind of have all of those values? Yeah. So this first one we're going to say is f of x equals -3 times the absolute value of x minus 2 plus 4. Easy peasy, lemon squeezy. Okay. If we take a look at example B over here, kind of the same idea. I've been given the vertex, okay, which is right here, and I know that that is the ordered pair HK. I've been given an additional point that's on the line, so I can use it to figure out the slope, which means that I can find the value of A. So A in this case, I know is going to be positive, right? And I know it's going to be positive because it's opening up, okay? So it opens up. Where's this one opened down? So because it's opening up, I know that the value of A is going to be positive. So I went up 1, 2, 3, and I went to the right 1, 2. So that's going to be 3 halves. So my slope is 3 halves, and that's the same thing as my value of A. So I have A, I have H, I have K. Let's write a function. We'll call this one g of x. Okay, so g of x equals positive 3 halves, so I just write it as 3 halves, times the absolute value of x. This time, though, it's going to be plus 3. Why is it going to be plus 3? Because that's negative, and we take the opposite sign. Okay, so x plus 3 minus 2. So again, we're confirming that we've got the vertex at -3, -2, bam. That we've got a slope of 3 halves, so up 1, 2, 3, to the right 1, 2, bam. Right on that point, we are good to go. All right, so last thing we're going to go and take a look at. Applications of absolute value. So again, what are applications in an Algebra 2 class? Word problems. So our word problem here says that a raincoat retailer has modeled the number of raincoats sold from January through May by the function r equals -30 times the absolute value of t minus 3 plus 80. Assume that t equals 1 is January. So it's kind of going by month, right? What is the maximum number of raincoats sold in 1 month? In what month is this maximum reached? All right, so let's go ahead and let's graph this function. All right, so if we're going to graph it, there's a couple of things that I probably want to know. I need to know where the vertex is. So looking at this function, I can tell the vertex is going to be at +3, +80. Okay, so +3, +80. So I'm going to go to this little graph that's over here that's already done for me, where I've got the months and then the number of raincoats sold, and I'm going to go to 3 and all the way up to 80, which is what? 60, is that 80? Yeah, that looks like 80 to me. So 3 and 80. So we're going to put a little dot right there. Okay. What direction is it going to open? Well, to determine that, I need to look at the value of A. Is it positive or negative? It's negative, so it's going to open down. Okay. Then to figure out what the slope is, I'm going to look at that value of A. That slope is -30, so its slope is -30. Okay, so from this point, I'm going to go and graph something with a slope of -30. Well, what's 30 less than 80? Well, 50. So I'm going to go down 30, which takes me to 50, but I'm going to go to the right 1 month, and I'm going to go right about there. Okay, then from this point, I'm going to go down 30 and to the right 1 more. All right, I can't really go further, but I could kind of estimate where this graph is going to be going. So on the opposite side, because this is an absolute value, so it's got to look like a V or a flipped upside down V, I got to do the same thing going towards the left. So I'm going to go down 30, but now I'm going to go to the left by 1 month. Okay, then I'll go down another 30 and to the left by a month again. All right, so if I went and kind of connected those points, I could see that the graph is going to look something like this. All right, now I'm going to go ahead and tell you guys something. You see how I started putting arrows on these? I actually don't need those at all. Okay, no arrows. Arrows would be a bad call for this. Why would arrows be a bad call for this? Well, let's look at the problem in context, right? This is the number of raincoats sold. Is it possible to sell a negative number of raincoats? No. Okay, you can sell 0, but you can't sell -10. Okay, so because it's impossible to do anything with a negative number of raincoats sold, we don't need arrows. We can just kind of stop it right there. All right, so we've got our graph. We've got some points that are plotted on it, and it's asking us to also fill out this little bit of a t-chart. Well, maybe I already have some of this stuff done. So when t, the time in months, is equal to 3, that's going to be down here. Okay, so here's our t, and this is going to be our capital R. So 3, how many raincoats are we selling? Well, 80. Okay. When it's 1, how many raincoats are we selling? Well, 1 is 20 raincoats. And 5, well, how many are selling at 5? Well, also 20 raincoats. Okay, again, just look over. All right, so we've got this table filled out. But it says, assume that T equals 1 is January. What is the maximum number of raincoats sold in 1 month? Well, what's the highest number on here? Well, if it's me looking at it, I'm going to look at the top of that mountain and say, blam, that guy right there. Okay, so max sold is going to be 80. Okay, in what month is the maximum reached? So the maximum sold is 80 raincoats in, and use your fingers to count the months if you need to. 1 is January, 2 is February, 3 is March. Okay, which is kind of surprising. You would have thought it'd be April, with all the talk about, like April showers bring May flowers and stuff, but no. They sell the most number of raincoats in March. All right. So, have we answered this particular question? Yes. We know the maximum number of raincoats that were sold is actually the vertex, which kind of makes sense. Do we even have to do the graph to find the vertex? Not really, if we know the function. And in what month is the maximum reached? Well, the 3rd month. Oh, the 3rd month, because it shifted 3 units over to the right. So, while the graph is helpful for us to visualize, it's not necessarily 100% important for us to do that to actually answer the question. So that begs, why would we even need to bother graphing this? Well, say you work for this particular company and you are being put in charge of ordering, say, rubber to go and make these raincoats. Well, when do you probably need to order the most? Well, I would say during the first 3 months of the year. And when do you need to order significantly less? Well, probably after the first 3 months of the year because the demand is going down. You wouldn't want to go and order the same amount of raw materials every month unless you really want to pay to store all of it until you're going to go through and sell the most number of raincoats, kind of February, March, and maybe a little bit into April. Okay, so um, today, just to review, we've gone over how it is that we're graphing absolute value functions. We've got a parent graph that looks like the letter V with a vertex at the origin. We can see how certain transformations can be applied to that parent graph that are identical to the transformations that you have done to every other function that you've ever learned how to graph. Okay, the reflection comes from the leading coefficient here, this value of A. If it's positive, it's normal. If it's negative, it's been reflected over the x-axis. If its value is greater than 1, it's been stretched, so it's skinnier. If the value is a fraction or decimal amount, then it has been shrunk. H is our horizontal shift, K is our vertical shift, and as always, the vertex will be located at HK. When we graph, we can just kind of apply all of those. And for absolute value graphs, we can really go through and just use the slope to find consecutive points on either side of the absolute value graph. Okay? If you're given a graph, you can just kind of work backwards. You can identify the vertex visually. You can pull out the values for H and K. You can use consecutive points to find the slope and put all of that together to come up with a function for your absolute value graph.